Hi, welcome to the second lecture on order topology. Possibly this will be the final one. But before I start, I would like to profusely apologize to those students who attended the order topology lecture 1. Due to various time constraints on my part, I couldn't schedule a Zoom meeting with you guys. Okay, but then I just wanted to finish this topic, and whatever time is convenient to me, I just wanted to go ahead with that. I hope you understand, but stay tuned. I'll invite you again for some other lecture, right? Again in topology if you want. Okay, so let us get started. Yeah, so we are defined in the last lectures about X is a set, this is a total order, and we define tau O order topology. Okay, and it has as a basis the elements of the form a comma b, a b in x and a less than b, along with possibly m b, where m is the minimum, b is in x, if m exists, minimum m exists, and union a capital M, a capital M, a in x, if max m exists. Okay, right. So what we wanted to do is we wanted to look at some examples we looked at. Now let's look at, remember my policy is always, whenever I introduce a topological space, the first thing I look for is take some strategically chosen elements in the set and look for the typical, simplest or minimal, or intuitively good looking open neighborhoods of that point. This is the trick which you also should learn. Almost all topological questions can be answered if you learn very early in your course this point. Okay, right. So let us look at the examples. So let us take with R2 with tau O, where is the order is total dictionary order. Okay, therefore if I have a point, let's look at, so this is my R2. Okay, now I have a point, a comma b, this is the point. Now what do I want? What do I want is the simplest open sets containing. Now that we had already defined look at bases, so we can just look at what are the typical basic open neighborhoods of AB, right? So what is that I have to do? I have to do something like alpha comma beta, open interval, and gamma comma delta. This must be in R2, this must be in R2, and so that my point a comma b lies in this interval, right? This would mean alpha comma b, beta should be less than a comma b. What does that mean? That means either alpha equal to a, in that case beta should be less than b. Do you understand? And similarly gamma a comma b should be less than gamma comma delta. Are you following? Alpha comma beta should be less than a comma b. So what are the possibilities? If alpha is a, then beta must be less than b. And similarly I have a comma b should be less than gamma comma delta. You understand? So in case my gamma equal to a, then what should I have? B must be less than delta. You understand? So that means I can keep the first x coordinates the same, namely a, and allow only the y coordinate to vary. That means I can have an open thing like this. This is a minus epsilon b. I'm sorry. I want beta should be less than b. I'm keeping A fixed, right? I totally forgot about that. So that could be A minus B epsilon, and this could be A B plus epsilon for any epsilon positive. You understand that? So my alpha comma beta is A comma B minus epsilon, because my beta should be less than B, and gamma delta, gamma equal to A, therefore delta should be strictly greater than B, make it B plus epsilon. Do you understand? So these are the basic open sets. Do you understand this? So the simplest open sets, okay, are open neighborhoods of the point A comma B are of the form the interval A minus epsilon, A B minus epsilon from this point to this point A B plus epsilon, this interval. But it's easier to look at the picture so that you understand what is happening. Yeah, right. Is that clear? Let me just check whether recording is going on. Yes, right. So immaterial of what point I take, what all I have to do is I just to move around the y direction a little bit back and forth. That's it. Then I got an basic or simplest open neighborhood of that point. Do you understand this? Now something very interesting happens, right? Now on R2 I have two topologies. So the question I can ask is, on R2 I have two topologies. Tau u, this is the usual topology induced by either D1, D2 or D max metric, or the other one is tau o, the order, the dictionary order topology, right? I want to know whether there is any relation between them. Yeah. Now remember, what are the basics open sets? Basis for usual topology consists of something like, depending upon which metric you chose, for example D2 metric, it will be open disk of this kind or open rectangles of this kind, for if it is D max, and this is with respect to D2, and with respect to D1 it will be something like this. Okay, this will be with respect to D1 metric. You understand? So let's stick to one. All right. Okay. Are you following? Okay. Now what are the basic open sets containing BO? We just now saw that. Okay. Given any point AB, right? All I have to look at is, this is the simplest ones, namely A B minus epsilon to A B plus epsilon, this one. So let us call this as a name, okay, U epsilon of AB. This epsilon affects only in the B direction. Okay, you understand this? So this collection as A comma B varies in R2. Okay, pause, review, proceed. So again, don't worry about this, keep the picture in mind. This is the kind of things, okay, you should have. Right. Now what do you see? Now you start with any open disk or open rectangle. Okay. So here, okay, this is open in tau u. Do you see that it's open in, these are open in tau o? Do you see that? Because I take any point here, then I can go back and forth, right? Are you following? Do you think you can give a rigorous proof? For example, if I look at, let me look at P equal to AB, okay, and I am looking at R positive, right? Now let's look at A B minus epsilon, A b plus epsilon. Okay, let q be any point in this interval. Then q of the form a comma t, where t is b minus epsilon less than t less than b plus epsilon. Yeah. Now when does q belong to BPR? Okay, let's with respect to any another metric. Okay, let's look at D max metric. Then that means the maximum of the distance. What is that? P is a comma b and q is a comma t. Therefore, it is 0 or mod t minus b. That should be less than r. You understand that? Yeah. But what do I know? Mod t minus b is less than epsilon. Therefore, what I need is epsilon should be less than r. Right? Therefore, if I choose any epsilon less than r, this basic open set, okay, this is basic open set u, okay, of a comma b, that let me call it as, I am calling it as p and epsilon. This is contained in BPR if epsilon is less than r. You follow that? Therefore, what I have shown is any, okay, typical or simplest open neighborhood. These are actually basic open sets. If of a comma b, okay, right? Sorry, a comma b in R2 with the usual topology are open in tau O. And hence what we conclude is tau u is contained in tau O. Okay, pause, review, proceed. So the ordered topology is finer than the usual topology. Okay, right. But notice that this is the simplest open set, right? A comma b, this one. Okay, this is my u of p comma epsilon. This is in tau O but not in tau u. Why it's not in tau u? Because given AB, the typical open neighborhoods of AB in usual topology will be either open disk around AB or open rectangle around AB, and that cannot be contained in the simply vertical line. You understand? Therefore, what do I have concluded? Therefore, conclusion, tau O is strictly finer than the usual topology on R2. Okay, pause, review, proceed. Right, but just I want to show you something interesting. Okay, in the case of R, let's look at, okay, this is just a remark. I wanted to learn these things, you know. Many of you learn subject only for exam point of view, but if you want to master the subject, you should always go back and forth. Earlier examples, future examples, sometimes if you have heard about them, and the current example, present example, all of them you should look at simultaneously, try to get more and more insight. Now if you notice this in tau, the basic open sets are of the form a comma b, right? And we know, and we also know the usual topology. This is the usual topology in R. Okay, and this tau u is, tau L is finer than tau u and strict. Okay, you understand that? Any open neighborhood in tau u, this is also in tau L, but not the other way around. But on the other hand, Q, the set of rational numbers, is dense in tau u. This is your real analysis theorem, density of rationals, right? But it's also dense in tau L. Usually, okay, this is just a remark, If you have difficulty, you can ignore. Suppose I have set X, I have two topologies tau 1 and tau 2, and assume tau 2 is finer than tau 1. Okay, then if I have a set D, subset of D, suppose D is dense in tau 2, that will mean D is dense in tau 1. The first topology, the coarser topology. That's because when do I say D is dense? Okay, give me any non-empty open set U in tau 2, then U intersection D is not empty, right? This is the definition of D being dense in X tau 2, right? Now suppose U, let us say V is in tau 1, then V also belong to tau 2. Therefore for every V in tau 1, V intersection D is not empty. You understand? Therefore if D is dense in tau 2, D is dense in tau 1. This is, we have proved it. Yeah, but okay, but D may be dense in tau 1, but it may not be dense in tau 2. It may happen. So it's something, is a rarity. Something dense in a coarser topology being dense in a finer topology is a rarity, and that's what happened in the case of lower limit topology. Q is dense in the usual topology, but usual topology is strictly coarser than the lower limit topology, but Q is still dense in the lower topology. That's something like a rarity. Okay, let me just write it so that you remember this. This is a rarity. Okay, the usual norm is the other way around. Now that I have done this, can you guess what I am going to ask next? What should be the next question? If you learn this, what should be the next question? Okay, let's look at Q squared, that is Q cross Q. Okay, this is dense in R2 with the usual topology, right? I want to know, is Q2 dense in R2 with the dictionary order topology. Alright, but that's an easy thing. Now that you know how to look for the simplest open sets, okay, so what does it mean? You give me any non-empty open set, U in tau O, U not empty, then U intersection Q squared must be not empty. This is what I have to check. Yeah, right, but that's ridiculous because I start with A comma B, right? Let me assume A is not in Q, the simplest open set containing this or this form, right? So all the points here will have the same coordinate A, which is not a rational number. Therefore U intersection Q2 is empty. Okay, so if A is not in Q, then let me look at A comma B epsilon, this intersection Q squared is empty. Therefore Q squared is not dense in R2 with order topology. Do you understand this? So this is common, this is to be expected as a rule. Okay, this, but I am sure you should ask related questions. Now that I know Q2 is not dense in R2, but let's look at, you give me any A, B, okay, the simplest open sets are of this kind. Either A has to be rational or B has to be, A has to be rational or not, right? Suppose A is rational and B could be anything, right? Therefore you can see, or if B is not rational, let's look at this. Okay, R minus Q union R minus Q. Do you understand this? Don't get intimidated. It says if A is there, I want rational numbers should be there. If A is rational, then take irrational numbers. So there should be one irrational number here in this interval. Similarly, if A is irrational, I can take one irrational. Are you following? Is it done? This is one set, okay? D1. Is this done? Is D1 done in tau O? I can also think of something else. So Q squared union R minus Q squared. You understand what this means? That means it is set of all x1 in R2 so that x and y are both rational or x and y are both irrational. Is this done in L2? Is this done in auto topology? Again, if you look at the picture, this picture will immediately tell you it's a child's play now. You understand? That is why you know, don't just because you learn the definition, don't just go ahead, play with it for a while. Look at some simple examples. Okay, so pause, review, proceed. Okay, now let's look at another thing. We had already defined an adherent point of a subset A of a topological space x tau. Let me just recall. So I say x in X is an adherent point. This is called a K limit in my metric space lectures. K limit point. Okay, limit point. Okay, right. In my book, it's called limit. Metric space book, I call it limit point. Okay, but nowadays many people think of limit point as something else, so I decided to adhere to the point adherent point. Okay, if for every open neighborhood U of X, U intersection A is not empty. So the picture is, this is my A and this is my A, this is my A, this is my X. Take anything. Okay, this is my X and this is my U and this is my A. This is A, this is U, right? Okay, now let's look at, just to have a good understanding of order topology, let's look at adherent points of something. Let's take equal to I2. This is 0 1 cross 0 1 with order topology tau. Okay, I'll just give only one or two examples just to quickly see how to work with it, right? Okay, let me take this set. This is not, it doesn't look like a square, but believe me, okay, if you don't like, let me just ignore that. Okay, let me see whether I can draw a square. No, it still looks bigger, right? Anyway, it's all right. Okay, this is my square, right? Now let me look at only this set as my A. So what is my A? A is set of all x comma y in X, so that y is 0 and 0 less than x less than 1. So this is only the open line segment, right? Part of the x-axis which are there, right? So I want to know, okay, now let's look at 0 0. Okay, this is my point. Is this an adherent point? Now what is the question you should ask? What are the simplest open sets which contain the point 0 0? But we know they are, we had already seen it in the lecture. Do you remember that? They are of the form here. Okay, the simplest open sets are open neighborhoods of 0 0 in I squared with a tau order topology are of the form close 0 0 to 0 epsilon. So in our earlier notation it is u 0 0 epsilon. That is only the y coordinate keeps varying. You understand? So this object, let me call this point P as 0 0, then up epsilon, okay, intersection with the set A is empty. Therefore 0 0 is not an adherent point. Okay, pause, review, proceed. Now let us look at, for the same set, now I can ask, let us look at 1 comma 0. Is this? Yeah. Now let's look at the picture. This is my 1 comma 0, and we had already seen, yeah. So what, any typical say, simplest open sets, open neighborhoods of 1 comma 0 is of the form, I have to start somewhere. We had already seen that last example, right, in the last lecture. It has to start from some 1 minus epsilon to this open here, and all these lines are going to be there, and this okay, and something should be there. Okay, all these things will also be there, and it will start from here and from here, right? Are you following me? So I'll just only draw from here. This is my 1 comma 0, and it will go up to something here. Yeah, and all the in between lines will be there. Complete vertical lines which are squeezed between these two will be there, right? Okay, so naturally, so call this anything, any such open neighborhood intersects A non-trivially, right? Therefore 1 comma 0 is an adherent point. Point of what? A, right? Therefore if you look at the A closure, that is the closure of A in order topology, this is something like this. I just want to make you visualize the thing. If you want, you can write it. It is set up, it is equal to, you can write it, of course, x comma y. Okay, and what do you want? X is positive, x comma y in where? In x, I squared, set that on 0. What do you want? X, okay, x comma 0. So let me write, x must be 0 less than x less than 1, and y must be 0. No other point can be there. You understand that? If I start with any other point here, okay, I can always draw something like this. Another will intersect. So the only adherent points is going to be only the point 1 comma 0. That is an adherent point which is not in A. The only adherent point which is not in A. And if you know what is meant by a cluster point, okay, that's also a cluster point. Okay, please think. Okay, pause, review, proceed. Okay, now on the other hand, let me look at some other thing now. So in the same square, right, now let me start with something like this, a vertical line. Let us say this is equal to x equal to half. Okay, that's my A equal to x intersection x equal to half. Okay, but I am not assuming I'm on the and x should not be equal to 0. not sorry, y should not be equal to 0, y should not be equal to 1. These endpoints are not there. Yeah. Now let me see, this is a point half comma 0, this is the point half comma 1. Yeah. Is half comma 0 an adherent point? Okay. Yes, that's very clear. Why? Because any adherent point, any simplest open neighborhood of 1 comma 0 will start somewhere here and it will go up to here, right? So it will always intersect this line. Do you follow that? Yes or no? The answer is yes. Okay, so this is the way you have to play with it. I hope there are a lot of you can think of some more things and play with this. Okay, I think that's more than enough. Let me go to one more interesting thing. Okay, the last one. Now let's look at x with an order and let y be a subset of x. Okay, now since there is a total order, I have an order topology tau on x. Let me say this order topology, I don't want to call it tau o, order topology. Okay, if you want, tau x on x. This is order topology. Okay, now do you see that on y there exists two natural topologies now? Can you see this? Because y is a subset of x. Okay, there is a subspace topology. Okay, one is subspace topology, call it tau s on y. And what is the other one? Other one is, see, whenever y is a subset of an ordered set, okay, y also has a natural order, natural total order. What is that? If you give me y1 and y2 in y, then y1 y2 belong to x, therefore I have an order. y1 is less than y2, or y1 equal to y2, or y2 less than y1, right? There is a total order. Do you understand that? Therefore y inherits the total order on x. Therefore y is also an ordered set, y, and we again denote it by this. Therefore y, this is an ordered set. Therefore I have second topology, I have tau o, the order topology on y. Do you follow that? Please think about. So right, so I start with a set x which is ordered, therefore I have ordered topology tau x on x. Now y is a subset of x, therefore I can think of the y as with the subspace topology. That's one thing. Second thing is, okay, the order on x induces an order on y, which is also total order, right? Therefore I can give the order topology on y. Therefore I have two topologies on y. I want to know whether there is any relation between them, whether they coincide. Okay, there is an analogous question, but usually except my book, I don't think many books even discuss that. Okay, do you remember? I am not kind of go only the narrow way. Okay, look at something related, analogous result, and try to compare and contrast so that your understanding is deeper, more okay, intensive. See, let us look at, suppose xd is a metric space and y is a subset of x. Then d induces a metric, right? There is an induced metric, okay, on y, induces a metric on y, namely distance between y1 and y2 is same as distance between y1 and y2 when I consider y1 or y2 as elements of X, right? Therefore now I have the metric topology on X on X. Therefore on Y I have two topologies, natural topologies. What are they? Namely, okay, I can think of this YD as a metric space and hence the metric topology on Y. And second, Y I consider as a subspace of X, therefore I have the subspace topology. You understand? Yeah. In the metric space case, these two topologies are coincident. The metric topology and the subspace topology coincide. It is due to the basic observation. You can look into my metric space lectures as well as metric space book. Basic observation which is needed to prove the following. Suppose this is my X, okay, this is my Y, okay. Now suppose this is start with a Y here or Y here, and this may be my BXR. This is a open ball with the center at Y, radius R in X. You understand? And then you can also ask what is BYYR. Okay. Look at all points in Y which are at a distance less than R. This is my Y. This is not the point, sorry, this is not, this is my Y. Okay. And this is nothing other than BXYR intersected with Y. So this is the, so this is your BYYR. You understand? From this observation I can conclude this. Okay, I leave this as an exercise. Okay, so prove this and hence conclude. Okay, tau is tau d. Or also you can look into my book, but I am sure now all of you are good, right? You should do on your own. Okay. So what you have seen is on a metric space, on any subset there exist two natural topologies, and luckily in the case of metric space both the topologies coincide. Now I want to know what happens in the case of order topology. So let's go back to the earlier case. So case on hand is X ordered space, Y is a subset of X, then on Y I have two topology. One is order topology, the other one is subspace topology. Okay, subspace topology consists of all elements of this kind. I hope all of you know that. Okay, right. Let us look at the simplest case so that no, we'll do that. So let us look at R2 with order topology tau O. My Y is the x-axis, that is x comma y in R2 with y equal to 0. Right? Now I want to know what is the subspace topology and the order. Right? Now let's look at on Y what is the order. So I am given 2 points x1 comma 0, x2 comma 0. Okay, these are points on Y. Therefore x1 must be less than x2 if and only if the order topology x1 0 is less than x2 0. Do you understand this? When I say with respect to the induced order x1 0 is less than x2 0, that only means x1 must be less than x2. It's usual, right? Therefore the order topology tau O on Y, okay, the basic or simplest open neighborhoods are of the form, this is it, that is the intervals are the form x minus r comma 0, x minus epsilon comma 0 up to x plus epsilon comma 0. This is the open rule. This is my x comma 0, this is x plus epsilon x minus epsilon comma 0, this is x plus epsilon comma 0. Understand that? Therefore, in some sense, intuitively, the order topology on the x-axis is nothing other than the usual topology. Do you understand? It's intuition, right? Therefore, tau O on the x-axis coincides with the usual topology. That, what do I mean by that? On R2 I have the usual topology, right? And consider my x-axis y as a subset of R2, then the subspace topology on y induced by tau u is the usual topology. Okay, so these two topologies are the same. Okay, pause, review, proceed. Right, now let us see tau on R2 induces the subspace topology on y, right? So what are the simplest open sets? So this is my y. The simplest open set containing this are the form this. You understand that? So I take u x comma 0 and epsilon and intersect it with y. These are the simplest open sets. Open neighborhoods, okay, in the subspace topology on y induced by the order topology on R2. Okay, keep the picture in mind, don't get psyched by my words, right? But what is this? That's nothing other than singleton x comma 0. You understand? Therefore, singleton x comma 0 are open in the subspace topology on y induced by the order topology on R2. So in particular, okay, wow, what have we got? The subspace topology on the x-axis induced by the order topology on R2 is the discrete topology. Yeah, whereas he induced the order on the x-axis, and look at the order topology on the x-axis, it is nothing other than the usual topology. Do you understand that? Please go through it, revise and discuss with your friends so that you are very confident. If you have learned all these things, you would have mastered order topology. Okay, believe me. So we come to an end of the order topology. I hope all of you enjoyed, and some of these things are now done well, and keep the picture in mind. Okay, do not be psyched. Okay, in the last one, what did you look at? You looked at the x-axis as part of R2. Now R2 we had the order topology. Then what did we look at? We induced the order on the x-axis. Then it turns out to be usual order, whatever it may mean, and therefore the topology, okay, the order topology with respect to the induced order on the x-axis is nothing other than the usual topology on the x-axis, right? But look at the subspace topology on the x-axis induced by the order topology on R2, it turns out to be discrete topology. Okay, try to learn, think twice, okay, go through that, discuss with your friends. If you have gone through these 2 lectures, you will be absolutely confident about order topology. In fact, you can teach a lot to others. Okay, are you excited? I hope so. Yeah, okay, take care, stay safe, we'll meet again.